teach about quantum computing, some basic concepts of quantum computing integrated with the quantum mechanics. First of all, I tell some what is the basic of quantum computing. Quantum computer don't use a usual bits, that is the classical bits. Classical bits is nothing but zeros and ones. Zero is 0 voltage and 1 is 5 voltage. Quantum computer uses qubits. Qubits is the quantum computer usually uses valence electron of phosphorus atom as a qubit. The qubit in qubits, spin up is 1 and spin down is 0. Where qubits have a special property called superposition. In our environment, there is a more thermal energy. So the valence electron of phosphorus will not be in spin up or spin down state. It will be in both the states simultaneously in atmosphere. But if we want to know the exact spin of the electron, we want to cool our environment to some minus degree kelvins to measure what qubit is this, that is spin down qubit or spin up qubit. Naturally, if we cool down the environment, our result will be spin down. Always it will be spin down. If we want to spin up this electron, we want to pass some microwaves. So the electron will go to spin up state. For measuring the qubit state, that is spin down or spin up, we use some magnetic field produced by some superconductors. We also use the nucleus of phosphorus atom. Using the spin of nucleus of phosphorus atom also we can measure this spin because it produces the internal magnetic field, and the external magnetic field is produced by the superconductors. Using this we can measure the spin, what the electron is spin up or spin down, but default it will be in spin down. So at the end the output will be 0 or 1, but it will be in superposition. Naturally it will be in superposition, but if we measure this, it will be in 0 or 1 state. Let us consider this as a lost valence electron of phosphorus atom. If this atom is in spin up state, it will be excited to the higher energy level. That is, this is the lower energy level. So if the spin of the electron is in up state, the electron will excite to the higher energy level. So because of this exciting to the higher energy level, in the transistor, here the transistor, between two transistors we will have some silicon atoms. In that we have only one phosphorus atom. If the electron spin in the phosphorus atom is in up state, the electron will be excited and it will produce a current flow. Using this we are determining that the electron is in up state or down state. That is, if the electron flows, we determine that the phosphorus atom's electron is in spin up state. If no current passes, we determine that it is in the spin down state. Normally, the nucleus is surrounded by an electron cloud where all the electrons are present. The electron cloud is a spherical shaped cloud. So we use Bloch sphere to identify the exact position of the electron where the electron is present. If we find the position of the electron, we can measure the spin of the electron. Here we have three coordinates because the sphere is a three-dimensional object. We have three coordinates z, y, and x. If the electron spin is aligned to z coordinate, it is said to be in spin up state. And if the electron spin is totally opposite from the z coordinate, it is in spin down. It spins down state. Here the position, by calculating the position of the electron, we will get some complex numbers. Here to find the state of this qubit, that is spin up or spin down state, we represent the state in this moment psi alpha 0 plus beta 1, where alpha represents the position of the electron, that is qubit, position of the qubit corresponds to 0, and beta represents the position of the electron which corresponds to 1. Here alpha, for example, if alpha is equal to 1 by 2 plus 1 by 2i, these two numbers will be in complex numbers, the magnitude of which gives the probability of being in that state, where alpha square is equal to a square plus b square. So here 1 by 2 the whole square plus 1 by 2 the whole square, which is equal to 1 by 4. 1 by 4 plus 1 by 4, which is equal to 1 by 2. So for this electron is have chance to be in the zero state, that is spin down state. Likewise, if we take the magnitude of beta, that is, if for example 1 by 2 is the magnitude, 1 by 2 is the value of beta, the magnitude of beta is equal to 1 by 4. So the electron has 1 by 4th of the chance to be in spin up state, that is one state. This is for one single qubit. To find the probability of two qubits, we have this formula where alpha 0 gives the probability of these two qubits. 0 represents that the first qubit is in down state and the second qubit is also in down state. Magnitude of alpha 0 gives the probability of that the first qubit is in down state and second qubit is in up state. Magnitude of alpha 10 will give the probability that the first qubit is in up state and second qubit is in down state, and magnitude of alpha 11 gives the probability that the first qubit is in up state and second qubit also in up state, where magnitude of alpha 00, where alpha 00 is equal to, for example, 1 by 2 plus 1 by 2 I. Alpha 00, magnitude of alpha 00 is equal to 1 by 2 the whole square plus 1 by 2 the whole square, which is equal to 1 by 4 plus 1 by 4. So we get 1 by 2 probability, where there is only half chance of first qubit is to be in down state and second qubit is in down state. If we want to find the probability of the first qubit is only in down state, the second qubit may be in various states, but the first qubit is in down state, we want to add the magnitude of probability of 0. Probability of 0, which is magnitude of 0 state and magnitude of 1. This is cancelled because here the first qubit, the probability of first qubit is to be 1. So the magnitude of these two will give us the first qubit is in spin down state. The new state formed formed with this magnitude will be here a square root of this magnitude is given to optimize the values. This is the vector rotation that the electron to be in spin down state, and this is the vector rotation that the electron to be in spin up state. The corresponding matrix representation is 1 0 and 0 1. 0 1. Based on this matrix, the gates of performing based on the matrix representation. We will see the gates one by one. From the matrix representation. This is nothing but an identity matrix representation. Matrix representation of identity matrix. Identity matrix. The function of identity matrix is nothing. If we multiply any identity matrix to a matrix, the result will be same. The result won't vary. If we flip the matrix, if we flip the identity matrix, it will give us the negation matrix. Which is a negation matrix. It will flip the column. For example, here this is the negation matrix and this one is 1. If we multiply this matrix to this, we will get 0 as the result. So this matrix will flip the qubits. This matrix will flip the qubits. The gate used for this is negation gate, which is nothing but a NOT gate in classical computer. This is like a NOT gate in classical qubits also. One of that is C0 gate, which handle more than one qubit, 2 qubit gate, which is C0 gate split the qubit into two bits, control bit and target bit. The least significant bit is always considered to be the control bit, and the most significant bit is always considered to be the target bit. That is considered 2 qubit, 0 and 1. 0 is least significant bit and the 1 is most significant bit. Therefore, 0 is a control bit and the 1 is the target bit. Based on LSB, MSB will be changed. The function of C0 is, if the control bit is 0, the target bit remains same. There will be no changes in the target bit. If the control bit is 1, the target bit will change. If the target bit is 0, it will goes to 1, and if the target bit is 1, it will goes to 0. So based on the control bit, the target bit will be changed. If the control bit is 0, then this is not a matrix multiplication, it is different from matrix multiplication, where we will multiply each element of this matrix to that matrix. The tensor product representation of this vector is which gives the result as this matrix. Therefore, the matrix representation of this vector is this, and the tensor product matrix representation is this. Let us apply C naught gate for 1 0 is equal to C naught of matrix representation of C naught gate is which is nothing but an identity matrix where the last 2 rows are flipped. Applying this matrix to which gives us 0 1 0 0. Which gives us 0 0 0 1, which is nothing. Therefore, here the control bit is 1. Therefore, we want to flip the target bit. So, by applying the C naught matrix, the target bit is flipped. Next gate is Hadamard gate, which is also a single qubit gate. The function of Hadamard gate is to transform the normal state of qubit to superposition state. For example, this is nothing but it represents the electron is in spin down state, which is 0. If we apply Hadamard gate to this, it will give the superposition of half the chance of 0 and half the chance of 1. Previously, we see some lost here. In this, if the electron is in 0 position, that is, if the electron is here, if we apply Hadamard gate, the electron will be flipped and go to plus state. That is, the electron which is corresponding to z-axis will move corresponding to x-axis. So here the electron is in 0 position, which goes to the plus. That is, if the position of the electron is coordinate with the x coordinate, then the electron is said to be in plus. Which is a superposition state. The matrix representation of Hadamard gate is The matrix of Hadamard gate is derived from Hermitian matrix, where Hermitian matrix is nothing but Hermitian matrix. Hermitian matrix is nothing but if a matrix satisfies the condition, that is, if H is a matrix and which satisfies the condition which is equal to H transpose and H conjugate. If the matrix is equal to given matrix is equal to H transpose and H conjugate, then the matrix is said to be in Hermitian matrix. Initially, Hermitian matrix is used for converting 2D pictures to 3D pictures. After that, now it is used for changing the state of the qubits. If we apply Hadamard gate to 0, the result will be 1 by root 2, 1 by root 2, which is nothing but there is only half chance for 0 and half chance for 1. Where this is alpha and this is beta. So the magnitude of alpha and beta will give us the probability. Therefore, 1 by root 2 the whole square, which is equal to 1 by 2. Therefore, 0 has only half chance to be the electron has a half chance to be 0 and half chance to be 1. In diagram of C0 and Hadamard gate, if the state is 0, 1, if we apply C0 gate, it will be changed to 1, 0. Likewise, 0 minus 1 means if we apply C0 gate, it will be changed to minus 1, 0, vice versa. And if we apply Hadamard gate to 0, 1, the state will be changed to 1 by root 2 minus 1 by root 2 and vice versa. These two are the state transition diagrams of two gates. If we apply Hadamard gate to 0 function, the state notation will be and if we apply Hadamard gate to 1, the state notation will be using these gates only we build some of the quantum mechanical concepts in quantum computing. For example, using these two gates, C0 and Hadamard, we build entanglement, teleportation, etc. Let us see one by one. Here this matrix can't be split in the terms of tensor product. That is A, B, tensor product of B, B. This matrix representation can't be right. This matrix representation don't have an equivalent tensor product matrix representation. Therefore, the qubit corresponding to this matrix is said to be entangled. The circuit for entanglement is Here is the circuit. The circuit will change the qubit to entangled state. For example, if we apply hard NOT gate to this qubit and subject it to CNOT gate, this qubit will be entangled. For example, the mathematical derivation of that is, here H1 represent, we want to apply a hard NOT gate for only the first qubit, not this. This will change the qubit to tensor product of 1, 0, which is equal to CNOT representation. Therefore, here the 0 is entangled in this way. Now we are going to discuss about Dodge algorithm. Before going into that, we can discuss some functions. There are 4 types of functions here. Constant 1, constant 0, identity and negation. These 4 functions are categorized into 2 functions, where these 2 are categorized to constant functions and identity and negation is categorized to balanced or variable functions. Dodge algorithm is basically used to find whether the given function, the function inside the black box is a constant function or variable function. Where the classical computers take 2 tries to find whether the given function is variable or constant. Where quantum computers can make it in just 1 try. This is the circuit representation for finding whether the given. Here initially the states of the qubits will be 0 by default. So we are applying NOT gate for both the qubits. After applying NOT gate, the state will be changed to 1. The psi A state is given to hard NOT gate. So here the state will be changed according to the hard NOT functions. For 1, the hard NOT gate is applied. The equivalent vector notation will be this. This is the black box where we are going to perform the Dodge algorithm. Here the input from this hard NOT gate will be kept constant, but the input from this hard NOT gate will be changed to y C0 of function of x. Here the function will be applied to x and which will be subjected to C0 gate with y. First of all, the hard NOT gate is applied to both the states, this one and this one, and we combine those 2 states, we get all the possible four set of states, 0, 0, 0, 1, 1, 0 and 1, 1. 1, 1. Here, this 0 is x and this 0 is y. So, here x won't be changed, only y will be changed to x C0 of f of x. So, we kept zeros of x as it is and applying this to y. So, here y is 0. So, 0 C0 of f of x, x is 0. That likewise we are applying for all the things. After that, this is simplified to this thing. If we apply C0 gate, C0 gate between 0 and f of 0, there will be no flip. There will be the function. This will be not flipped because the LSB This is L as the least significant bits. Since the least significant bit is 0, there will be no changes. So we write this as f of 0. But if the least significant bit is 1, there will be changes in this f of 1. So we kept 1 plus f of 0 as f dash of 0, and 1 C naught of f of 1 as f dash. Here as the least significant bit is 1, we are changing f of 1 to f dash of 1, where f dash of 1 is equal to f of 0 and f dash of 0 is equal to f of 1. Substituting this to this will give this. Then we are separating the constants and functions. Here here the output will be b. Let's take this as b. Here the output will be b in the format of this. If we subject this into a hard AND gate, we get 1 by root 2 of 1, which indicates that the function inside the blackboard is balanced. If we get 1 by root 2 of 0, then the function inside the black box will be constant.
Now we are going to see how we are going to make some quantum computing stuffs using programming language. This is nothing but a Python programming language. Here in the first step we are importing Qiskit. Qiskit is the library where we have some predefined packages and functions kind of things to perform the quantum mechanical stuff. And here we are checking the version of the Qiskit that we have the latest version of Qiskit, and from Qiskit we are importing IBM Q library. Library. Here we are saving our account using the token to this code, and we are loading the our IBM Q account here. These are some prerequisites done to work with the real quantum computer, to give our program to the real quantum computer. Here we are importing all the packages of Qiskit, and here we are giving some variable. QR is the variable where we store the quantum registers. Here two represents that we are using two quantum registers, and in this CR variable we are storing the classical registers. We are giving two classical registers. These two registers are given to the quantum circuit and stored in the variable called circuit. Math.lib is the library imported to draw a circuit.
Here, the hash represents the Hadamard gate. The Hadamard gate is being given to the circuit through the register 0, quantum register 0, and the equivalent circuit representation is this. And here, CX represents the C node gate. The C node gate is given in between two quantum registers, and the measurement gate is given in between the quantum register and the classical register to measure the state of the qubit. Stimulated is the incorporated function in our systems to do quantum computing stuffs in our system itself. Here, the result variable stores the result of the circuit integrated with the stimulator. The plot histogram is the library used to plot the result in the histographical manner. Plot histograms the function, and the function we are giving our result. We are passing our result with the circuit to this function. By doing this, we will get write the result in a histographic format, which is nothing but the graphical representation. Here the result is that there is half a chance of being 0, 0 and half a chance of being 1, 1. That is the qubit is being the two qubits have half a chance of being 0, 0 and 1, 1, which is nothing but the qubits are being entangled. The above circuit representation is an